I'm going to talk about how do you actually implement this inference of material properties from the observed GV measurement, and eventually link that to process parameters. So basically, we do it in this called Bayesian network. So also you can call it a two-step hierarchical base. So what is a hierarchical model? For example, the family tree is actually a hierarchical model. You have the grandfather and grandmother, and eventually it leads to the grandsons. And this is deterministic, so it's not in any way Bayesian. But if let's say if we think about the blood type of the knowing the grandfather and grandmother have its blood has an A type blood, and then grandfather has B type, and then the kids is having different O, A, and B, and then you could sort of then you try to infer what is the blood type of the parents. Then this actually becomes a probabilistic question. And so this is relatively simple. And if you think about DNA sequencing, and then immediately this whole thing becomes hard to trace. So just to translate this sort of a family tree problem to whatever we have in the lab is actually for our day-to-day optimization in the lab, you're also facing a hierarchical problem, which is you have your process tools. In this case, we are looking at gallium arsenide, so we are using the MOCVD, the metal organic chemical vapor deposition. And what we are measuring typically is the electrical measure, GV curve, current voltage curve. And eventually, what we want to understand is actually the GV curve is the grandparents of whatever you changed in your process conditions. But the parents is actually whatever material parameters in the device. So so in the device, it's a multi-layer device where you have the contact, you have different capping layers, and you have parasitic resistance. So eventually, this whole thing becomes this tree structure. And the method we are developing is actually to map from these process variables to the hidden material descriptors, and then to the observed electrical measurements. So basically, this is what we are doing. And this is a Jupyter notebook example, so I'm gonna show you actually how do we code it. So all right, so the model consists of two main parts actually. So first of all is the neural network surrogate model for denoising the experimental GV curves and predicting the GV curves from the material descriptors. So why do we need that? Is actually this part is that we in the solar cell community we have very good device simulations, but but they are slow and they are hard to use actually. So it's sort of mimicking for example for the material discovery we sort of develop all this surrogate model to speed up the DFT. It's not to speed up the DFT, but just to do some pre-screening. So this is more using a neural network surrogate to replace whatever partial differential equation you have in the device, in the solar cells. And the other part is actually this two-step Bayesian inference, and how do you link the gross temperature to the material parameters? And this is where you can actually use your chemical intuition, and this is a kinetically this is a kinetic activity process. You could embed those knowledge into this whole framework, so making this whole algorithm become end-to-end differentiable. All right, so basically the first part is so Felipe just introduced is the surrogate model to map the material descriptors. So in this case, we are actually looking at the bulk lifetime, the doping, the interface recommendations to whatever you observed in the GV curves. So just to increase so we actually vary the light intensity just to get more information from the GV curve. And so basically, it relies on two neural network models. One is a denoising autoencoder. The other is a regressive model. So here we use just a standard machine learning model. So we first load in the libraries and dependencies. We can load in the data, and I will not run this because it's going to be slow. And this is actually how the data looks like. This is the current. This is the voltage. And afterwards, you could have, so afterwards, we actually built a denoising autoencoder to try to denoise like whatever experimental like noise you have in your data. So basically, that's the standard like CNN, and you just train that. And this is basically the results. Like the orange is the raw data. The blue is the fitted data using the autoencoder. So you could actually
interrupt. This doesn't look like a solar cell JV curve to me, or
oh yeah, so this is a JV curve, and then we actually have like multiple JV curves for the same solar cells.
What is the x-axis?
The x-axis is actually 0 to 1 volts, 0 to 1 volts, 0 to 1 volts. Yeah.
Different light intensity.
Yeah, different light intensity.
Zero, I mean.
Yeah, it's
it should go to 0. Where's the open circuit voltage?
Oh.
I see. Okay.
Yeah, this is basically.
The VOC.
Yeah. It's like because for translating that into a machine readable form, like we actually sort of concatenate like all the JV curves together. So basically, you have 5 JV curves, and then you put that into one same vector. So this is actually how the vector looks like. But you break that actually is in the 5
The noise is something you generated by your. This is all simulated. Right?
This is right now it's simulated.
But the noise is simulated too.
Yeah, the noise is simulated too. So right now we are just adding Gaussian noise. But later you will actually see it actually is used to denoise the experimental JV curves. All right. So now this is basically trained the denoising thing, and then we need to map the material descriptors to the to this JV curve, this concatenated JV curve. And like again, this is a performing a regression. I didn't complete it because it's just taking too long. And but eventually, like what we have is we have the MSE for the training set, which is the JV curve in the training, and then the test the MSE like in the test data set. So basically, you can see the value is really low. And if you just plot the trend and like the predicted using the predicted JV curve and the original JV curve is actually pretty much the same. And but the more important thing is actually the speed up of the computation time. So basically here is the full runtime. So this is in the log scale. This is like the full EXE run if you use this solar cell simulator. And this is if you do that in a Python script. And then if you use a neural network, this is and then you actually speed up this by like if you are using GPU, it's actually by at least like 100x. And the reason why we need to speed this up because when you actually perform the Bayesian inference, this is actually after we have the surrogate model, then we're able to perform this hierarchical Bayes where you already have a neural network to map the material descriptors to the model output, and then you embed your physics knowledge, whereas you know that like the MOCVD process is a kinetic process, and it should follow certain type of Arrhenius equation, like it should follow like certain like type of Arrhenius equation type of relations. So basically we have, this is basically captures the Arrhenius equation, B and C, and T to the power A is actually a pre-exponential factor. And what we want to know is actually what are the exact values of A, B, and C given the observations. So basically this is like a full Bayesian inference, and you can do like a Markov chain, like Monte Carlo sampling, MCMC, and then to fully recover the data, the original data distribution. And by doing that, you actually need like thousands or like 10,000s of runs. So in this scenario, like the speed up using a neural network really like helps to perform this full Bayesian inference. All right, so now like we could do the Bayesian inference. So first of all, we can look now our experimental data and with the experimental like variation. So in this case, we are varying the temperature in the MOCVD chamber. And these are the actual experimental curve, like normalized. And like after that we feed this thing into a denoising autoencoder. So this is how it looks like after you denoise that, and then you fit the whole thing into a MCMC framework, and then here we just define this thing into we define like the prior. Like in Bayesian inference, you have prior likelihood. The prior is whatever the Arrhenius equation you have. So basically, this is the parameterization of the Arrhenius equation, and the likelihood is actually the neural network, and this is just trained parameters, and then you can perform the full MCMC run. I just perform partial of that, and you will eventually see the loss starts to decrease with the number of runs, and you could sort of recover after knowing the ABC values, so the pre-exponential factor, the slope of how the slope of the slope inside the Arrhenius equation and the constant, and you can recover the curves. So basically that's for the experimental ones. It sort of recovers the experimental one except for this part, but this is not running because this is not running for a long time, and we could even plot how the material parameters. So in this case is the doping levels and the lifetime and the interface recombinations changes with the processing conditions. So the dark area is actually represents the uncertainty in your model, because this is in a Bayesian framework. You are not having a single value, you're having a full distribution of that. And by knowing that, actually, if you run it longer, so eventually what you will obtain is something like this. You will be able to know that for optimizing the solar cell performance, for example, we want to grow our bulk at this temperature. Well, we want to have our front interface at this temperature, while the rear interface at this temperature. So those are the informations you will not get if you perform traditional Bayesian optimization or traditional DOE, and this is essentially what you will be. So then this is what we did. We performed the actual experiment. So we make the gallium arsenide solar cells. So all the solar cells is with our ARC, and with different temperatures. This is basically what you would achieve with just a grid search, and this is what is the efficiency level you can achieve if you apply this Bayesian network method. And yeah, and eventually you will actually get the full distribution, which is the ABC values for everything, and the model becomes fully interpretable. So you know exactly how the material parameters changes with the temperature, and that's it.